Hello, I'm Sebastian Kazakov, and this is my scuffed edition of AP Computer Science Principles. Here's a disclaimer. This video is a short, overall scuffed explanation of AP Computer Science Principles topics. Because some of the facts are simplified, they might not be entirely accurate, but this will give you a good idea of what AP Computer Science Principles is about. I hope you enjoy it. Starting off with your hand. Your hand is made out of a huge amount of teeny tiny atoms. These atoms are usually made out of protons, neutrons, and electrons. The important thing to remember about this is that the proton is attracting the electrons in this kind of system, and you should really focus on this electron. So, proton is attracting the electron, neutron just hangs out here. It's important that you focus on this blue electron because it's the simplest thing in our universe, and although it's pretty simple, it does a very complicated but useful trick. When you line up several atoms like this, and you shove their electron, ripping it from the magnetic pole here to the next, so that it's magnetically attracted here, and you do this for several atoms, you will get an electric current. We call this electricity. Because we are pushing the electron and attracting it here, we get a general positive attraction here and a negative repulsion here. And this entire system can be simplified to this. Now, the reason why this works, and also the reason why some materials can do this while other materials can't, is because of these valence electrons, or outer electrons. You can read the above notes if you would like, or you could just listen to me explain. So, these materials that have small protons and very few outer valence electrons, they have a very weak pull. They're far away, there's not enough, quote, magnets here, and not enough electrons out here to stick to it. So it's really easy if I just took it and rip it off. And this is why electricity easily flows in these kind of materials, like copper. A lot of metals are similar to this setup. Maybe they have more protons and electrons, but they always have very few electrons out here, and they're very good at conducting. That's why they're called conductors, because they're good at having their electrons ripped away and moved on to the next. On the other hand, bromine is awful at this. It has a huge nucleus of protons, which is very good at attracting all of its electrons, so it's not letting anything pass it. It will take an immense amount of force to rip off even a single electron to let everything conduct. And this is why they are insulators. They do not allow electricity to happen. Then you have a pretty interesting type of atom. You have semiconductors. The most common and most used is silicon, but these are very important. They are by nature just insulators, but they have not too many, not too little electrons, and their nucleus is not too big, also not too little. So it's possible to rip it off, and although it's not as easy as this, where you can have a little bit of attraction and repulsion to get electric current, you need a lot of attraction and repulsion to get all the electrons flowing. So that is why it takes a lot more energy for a semiconductor. Now, if you wanted to connect atoms together, you'll see why this is important soon. They need to think that they have their own electron, but they're actually just sharing it. These two hydrogens, for example, this one can say that yes, this is its own, and this one can also say that yes, this is its own. But in doing this, they just connect to each other, and you get this kind of bond, which is a simplified model. Now, once again, this might seem completely random, completely out of place, but if we connect a bunch of silicon, which is a semiconductor, boron, which you can see by the 3 outer electrons, is a conductor, and you can see by the phosphorus, it has 5 outer electrons, so it is an insulator, and we get this kind of structure. The reason why this structure is important is because it does a very weird thing. When you have these outer valence electrons, this one has 3. It's not neutral like silicon. It has less electrons, so it has more positivity. That's why I colored it red. while here they have more electrons than silicon, so you can consider them negative. Electrons and protons want to stick together, so this phosphorus atom will gladly give up an electron just to keep things balanced. This one did not find a positive boron to be with. But even though it seems like we solved the problem here, we create a problem in the overall charges. Because even if all of this is neutral, the boron has 4 outer electrons now. This is not natural because it has its protons outnumbered by electrons now. And this one is lacking electrons for its protons. And this can be taken advantage of. If you try to pass electricity through here, you will not be able to. The electrons will stick to the phosphorus because it needs electrons for its protons, and the electrons will be repelled by boron because boron has too many electrons. It's already trying to get rid of one. Why add more? This is why it is an insulator. When you try to apply electricity from here, it's just not possible. But when you apply power to the, quote, gate, which is this boron, it takes that electron. If you put positivity over here, it sucks up the electron. It solves all the problems here, and electricity can possibly flow through. This system is called a transistor. The specific one that I just showed you is called an NPN transistor because this is over here, this is negative, positive, negative. And over here, it seems like it is negative because of what happens over here. So, the electrons, after everything cancels out, get repelled from here and they get attracted to here. But when you apply power, everything flows smoothly. Now, this is what a transistor looks like in real life. And this is a model I made for it, for simplicity. This is source, gate, and drain. Same thing here. We need conductors here, just simple ones, so that we can encase everything inside a plastic case, and so that we can have the same setup over here. Now, I can demonstrate again what will happen, that it will not be able to do anything until you activate it by powering the gate, applying electrons here to let the source go to the drain. And this can also be represented with binary. By putting power here, or 1, it does nothing, but if you apply power to both, you'll get a power at the end. So, we can take this that we learned from here, and we can apply it to the transistor. Now we are a lot more progressed in our understanding of a computer, because these transistors, even though they're just a switch with no moving parts, these switches can be linked together to start making some crazy logic. Over here I'm powering, here I'm not, here I am, here I'm not. A lot of nonsense going on. And for some reason, it's making more complicated outputs. Now, we can simplify things into logic gates. Over here, if I apply a charge, and here I apply a charge, it goes to next. But this is the second barrier. I need to power both of these legs. I need to power this leg and this leg. Over here, it can bypass that. I just need to power one and let one through and it connects out to here, or I can just power this and everything connects because I need this leg or that leg. Over here, it's the opposite. If I'm applying power, it gets sucked up and it gets sent to ground. And if I do not apply power, power can be easily put in another way. So this is not. And over here, this is just a buffer. If you apply, it is. If you don't, you don't. So it works kind of like a diode. So this same binary system for having 1 for on and 0 for off can be used for logic gates to convey their purpose. And this simplification of everything we have just done allows us to first make a number system for everything by converting our decimal system to a binary system where we can have 0, 1, 1, 0, something, 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 where whatever value we have, we multiply these two and then we add to every other slot. So let's say I put zeros for all the first 6. You multiply top and bottom, you get 0. Add them all together, it's still 0. And we have the last 2. If I put a 1 here and a 1 here, You multiply them both, you get 1 and 2. Add them together, you have 3. So 0, 0, 0, 0, 0, 0, 0, 1, 1 is equal to 3. This is how the binary system works, just like our decimal system that we normally use. If I put a 9 here and a 2 here, you're not going to be surprised. 2 times 10, 20. 9 times 1, 20 plus 9 is 29. Precisely how we would understand. And going back to our simplification of everything, and now having a binary system and a American Standard Code for Information Interchange, ASCII, we now have everything we need for a calculator. Now, this is a very simple 4-bit calculator. It can barely add and subtract, but it still can. We could input 9 plus 6. We can convert it to binary. And when we have all of this, we can get outputs. But this is very limited. If we go over what it can possibly show to us, which is 4 bits, so 1 times 8, 1 times 4, 1 times 2, 1 times 1, if we add all of this together, we get 15. If you get a result that's more than 15, this will be called an overflow error. It does not have enough slots to be able to represent this number. And these kind of calculators with a bunch of logic gates, they run algorithms, which take inputs, they convert it to binary. If it's addition, they do one thing. If it's not addition, they do another, and they convert back to a decimal to represent to us. Algorithms is any sequence of steps taken to reach a desired output. And with all our logic gates and all our prior knowledge, we can now take numbers and get numbers back. Here is something interesting though. Using all of these calculators, we can put them all together to form a computer. It is essentially a bunch of calculators that have a lot more freedom in what they're able to do. And at this point, when you have so many calculators working all together, to prevent overflow errors, they're going to obviously need to round. But when you round, you're going to slowly diverge from the true result. And this is something that turns into round-off error. And since computers are just really complicated calculators, you can start putting more complicated math. You got your lines, parabolas, trajectories, and then you have entire aerodynamic simulations. Now, this is all good and swell, but it's going to be very hard to represent. It is easier to represent, though, if we have pixels. Back then, they just had light bulbs, which were on or off, and these pixels, you could manually code each one on or off to draw a design. That's not fun, though. We could make it fun by using an RGB light-emitting diode, or RGB LED. If you use red, blue, green, you can make any color by mixing them together, and mixing the colors that they made together. Just mix all the colors and eventually you'll get every color you need. So we have 8 possible direct starts without mixing all the colors with the nearby neighbors, but we have all of this and we can hard code it by giving 3 bits. And a bit, as we said, is one of these slots. So over here we only needed 1 or 0, that's 1 slot, 1 bit. Over here we have 64 bits, so that's that. And there's 8 bits in a byte. So we have 3 bits per pixel. So each 3 bits here, each 3 numbers is 1 pixel. And this is the code that's necessary for this cool little background I made. If you plug this into a computer and you made sure that it was running, you activated the logic gates for the display, this would give you this exact result. Now, if you might have noticed, this is not fun to write. It takes you quite a while, but you can use programming languages, which are compilers that take human language, like cool draw design, yeah, this is a cool design, and it turns it into a lower level language, which is a little more complicated, which is a little more complicated, which is binary. So now all of this can be made with a single line, thanks to programming languages. This is cool and all, we can just control computers, do whatever we want with them, but this is going to be really hard to do if we want to communicate with other computers and tell them to do what we can already do. But we can do that by connecting them with a conductor, by inserting into specific logic gates, but it's possible. And the most common wire to do this is the Ethernet cable. So far, we've been using UDP, User Datagram Protocol, to send the data, which is just send it over, pray that it gets there. But if the connection gets interrupted or something else happened, then the data will be received out of order. To fix this, we have to use TCP, Transfer Control Protocol, which uses a handshake checking system where basically each computer makes sure that they're connected and they definitely sent over each message. So it double checks every step of the way. It's slower than UDP, but it will work even in horrible conditions. Now, if we're going to be working with a lot of data, not even TCP can save you if you have a huge amount of data being sent in one go and something happens. So, to fix this problem, we will need to start using packets, which are a chunk of teeny tiny bite-sized chunk of data with actual data in it, of course, and information about how it should be ordered, where it's going to, and other things. These other things will be important very soon, but this is how data should be transmitted so that we can transmit huge amounts of data in bite-sized packages so that things will work. And another advantage of doing all of this is that you get to save room on data, because the less data you can set over, the better. Now, if you don't compress anything, you could have this huge amount of fruits, and it just doesn't work out. But you can use lossless compression to take all of the original data, compact it by making a key of repeating values. So now I have a lot less letters here than this by just putting a general placeholder and telling what each placeholder is actually. This way I keep all my data, I reduce some of it to make it easier to transmit because there's less actual information, but it has the same value once you have all the key and you convert it back to this. So you lose nothing. Lossy compression, though, you're going to lose a lot of data, but you're going to have an extreme improvement of size. Over here, this is a lot easier to send over. It's barely any bits if you use the ASCII standardized system. But we just reduce everything to fruits and we're never going to know what originally they were. Now, if we want to do all of this that we were just talking about, if you do it the way I just explained it, you're going to need to connect every computer in the world to each other. This is obscene. The amount of wires is equal to computers times computers plus 1 divided by 2. This is not feasible. But there could be just one wire from each computer that goes to this thing called a router. A router will be able to connect inside of itself wires to each other based on how the computer wants, maybe even several at a time. But this saves a lot of wire. And you might have realized, how does it know which computer is which? This is why we need the source and destination IP address. IP, Internet Protocol. Internet is this network. Any network is just a bunch of computers connected together. And the biggest network today is called the cloud, or, as I said, the internet. Now this computer will know which computer wants to connect to, and the router will know how to do it. And it sends in the request to connect, and it randomly will send it off to another router, but if it is the router that is directly connected to the computer, it doesn't have to do it randomly. It will just send it right over. The reason why routers have to do all of this randomly is in case that routers get broken. So, what if a router gets taken out? This is why you need redundancy, several routers all working together, so that in case one router is taken out, you do not lose all connection like this. You have another that can still keep everything moving. Now, so far we've been able to do simulations, a couple other things, but it's not really that fun. We don't have websites. So, let's use a programming language to set up a website. Over here we have a title, we have 4 pictures, and a little comment I made. And yes, this is all good and swell. We have website, it can be sent over using hypertext markup language, and we have what we need for a website. But we can make it a little better by using CSS or cascading style sheets. Here we'll be able to define what exactly is what. It's going to make it look a little better. And JavaScript, JS, will be able to fine tune everything and make it truly unique in how you want it. Now, as I said, these programming languages, they're going to take some human understandable stuff. They're going to all work together to make a stupid amount of binary code and make your website. Because you have to remember, everything that computers do, it always comes back to binary. And in websites, instead of constantly having to use the same code that everybody else has used, what if you want to change some settings? You want to keep them for yourself, but you don't want to change them every time you open the website. This is why we have cookies. Cookies are little bits of data they can save into the background so that, well, coincidentally, when you set the background to pink, if you refresh the website, it's going to use the default code. So you're going to get a black background, but you want a pink background. So if you use the cookie will remember this. And when you refresh the website, it does not use the default code, it uses the cookie code. Now, at this point, when we have super complicated websites and we have a couple other things, we're going to need to have different things like routers that connect to servers. Now, servers are a bunch of computers all together that are very good at distributing the websites and sending the code to the computer so that they can use it. And this is how the World Wide Web is made up. Now, to send over all of this, we need to use Hypertext Transfer Protocol, or HTTP. Now, it would be all good and swell to send it over to website 95.291 something something, but it's even better if we can do a domain name system, which gives a nice human name to a website, like a very good flash game website on Doppler. Now, more likely than not, you're watching this from a device that does not need a wire going to the internet, like from your phone. Well, this is done thanks to Wi-Fi, wireless fidelity. This is a system that can turn electrical signals into radio waves and vice versa. Radio waves are a form of light and can be made with electric spark. The simplest possible radio you can make is a penny being tapped on a battery. You release electrical sparks, which release radio waves, which are a form of light, and if you're close to a receiver, it'll pick up the very weak signal. Now, Wi-Fi does a lot more powerful electric signals, and it communicates with the computer so that other computers from a router send data to the Wi-Fi block. It turns that binary data into radio waves, which your computer receives and turns back into binary. And your computer can do the opposite. Send binary into radio waves, into binary, and out to the router. But even if we have all of this, we can't have all nice things. Obviously, people are going to make things a lot harder to do. For example, if you are trying to pay to play a game, you will send over your credit card number and wham! Somebody can cut the wire and take it for themselves, or they can have a receiver for your Wi-Fi. If you send over your credit card number, they're easily going to take all of that binary data. So let's use a cipher. A cipher takes a message, and on the glance, if I didn't show you that this meant hello, you might not know that it means that. But using this key, you know that red is H, orange is E, green is L, and brown is O. So you have hello. Now, the problem is, how would you be able to send the key to someone without the key getting caught? Well, this is why HTTPS, Hypertext Transfer Protocol Secure, was made, so that using pure math, you will be able to use prime numbers and a public key number to have public encryption, not symmetrical key encryption, but public key encryption, where everybody knows that your public number is 92, and they like set up the letters so that they match your public number, but you will only be able to read the gargled mess by using your private keys and shifting the alphabet, for example, so that you can cross-link here and you can see what the message will be. Now, another way that is a little less technologically advanced, but is still very prevalent today, is by phishing. Not for like actual fish, but with a PH. You convince people to willingly hand over stuff by acting like you are an important authority figure, and you convince people that they should hand over information so you can, quote, help them, wink. So, most people are not that naive, though, so criminals need another way to do this. And they can do that by having websites that secretly hand over a cookie. This cookie will remember any information you type in and send it back to the bad people. And you go to their website, the cookie gets attached to you, and the cookie will send back anything you write. And they will be able to decipher your password using that. Now, if you just wanted to directly hurt someone, no complicated stuff, no stealing, you just want to hurt someone, you would use a DDoS attack, a directed denial of service, where you flood in a huge amount of requests for a website to just overload the computers. There's a limited amount. They can't handle everything. So if you overload them, they're out of the game. And to prevent a criminal, let's say they do get your password, to prevent them from doing anything important, you have to use multi-factor authentication, which uses something you know, something you are, and something you have, so that a criminal will need to get all of those three to be able to pass through, quote, an airlock. This way, only you, and uniquely you, can pass through this. But let's say a criminal wants to get revenge and profit at the same time. They can do this using malware. Malware are basically bad programs. Now, the programs usually use a Trojan horse method, like the legend, where a seemingly innocent thing is actually really malicious on the inside. So both ways, virus or worm, people are convinced to click. But a virus, when you're convinced to click, it quickly spreads to you, and then you become what you have succumbed to, and you spread it to other computers. The virus multiplies. Sometimes it does something, but usually viruses just want to multiply and spread. A worm, on the other hand, is a lot more direct. You click a worm, it goes into your computer, and then after it goes into your computer, it does not multiply. It just takes information, sends it back, and then it goes to the next victim. And today, as computers innovate, criminals and security on the internet fight, and life keeps improving, this is AP Computer Science Principles, Scuffed Edition. Thank you.